Hi everyone, this time I'm going to be introducing two equations that we're going to be using in our studies about mirrors, and I'm going to be going through some examples found on physicsclassroom.com on how to use those specific equations. So there are two that we're going to be going over today. So we first have this one right here. Okay. This is an equation that relates how far away the image and the actual image and the actual object are away from one another. Okay, so that's our first mirror equation. So if I want to identify what each of these are, this is exactly what you might be assuming it is. It is the image distance. Okay. And image distance just means that that's the where the image appears in relation to the mirror, or later on whenever we start talking about lenses, lenses. And the same thing applies right here. Whoops, that was ugly. This is the object distance. So this is how far away the object is from the mirror itself. And got a third one here. This squiggly looking F is no longer frequency, unfortunately. This is going to be the focal length. Basically, this is how far away the focal point is from where the mirror is. So that's just where the focal point is. Sometimes people use this F to represent a focal point as well, but we're going to be using it for focal length because that's the unit that we really care about. We don't really care about, knowing where the focal point. The second equation that I'm going to go over is going to relate the image height and the object height of the image of the object to its distance from the actual mirror. So whenever we have hi ho, it's off to work we go. Hopefully you have been working. Okay, so this is going to behave exactly as it did last time with the last equation, where h stands for height, and our subscript just indicates which one it is. The I is for image, and the O is for object. These again are the exact same as they were before. These are the image distance and the object distance. And these are all equal to capital M, which capital M is just a unitless number that represents a magnification factor. So if my image height would be bigger than my object height, meaning that like the image that's in the mirror looks bigger than the actual image itself, that means that it has a magnification of greater than 1, and that makes sense, right? Because you would be dividing a bigger number up here by a smaller number down here, and that gives you a number greater than 1. Now, let's say that your object height is going to be more than your image height. Well, then that would give you a number less than 1, and therefore your image height would be getting smaller, meaning that the magnification is less than 1. So let's go over to those physics classroom example problems, and let's go ahead and work through them. I actually think that it's going to be very useful for us to have both of these equations side by side whenever we're trying to work these out, because we're going to need to identify variables first and then start plugging things in. So take a moment to make sure you have your equations, and then we'll move on. All right, we are back, and this is our example problem from Physics Classroom. So I have a 4.00 centimeter tall light bulb. It's placed a distance of 45.7 centimeters from a concave mirror having a focal length of 15.2 centimeters. Determine the image distance and the image size. So I like to draw pictures for these. And here's our principal axis right here that's leading up to our mirror. We have a light bulb right here. And we know that our focal point is 15.2 centimeters. There's our focal point. And here is our distance for our object, okay? And we also know our height of our object is going to be 4 centimeters. Our distance is going to be 45.7 centimeters. Okay, so now it wants us to determine the image distance and the image size. So we've identified 3 variables, we're missing 2. I'm going to go ahead and I'm going to solve for my first variable, which is image distance. And the equation that I'm going to use for that is going to be the first one we went over, where we have 1 over the image distance plus 1 over the object distance is equal to 1 over the focal length. Now I can go over here to my diagram and see that I identified my focal length as 15.2 centimeters. And you can keep all these in centimeters, that's perfectly fine. It doesn't change your calculations at all. I don't know what the image distance is yet, so I'm just going to rewrite that variable. And my object distance I saw was 45.7 centimeters. Okay, so when I want to start to solve for this variable, it may be easier for you to convert all of these to a decimal. That's fine, works fine for me, but I'm just going to behave right now. I'm going to act like I'm subtracting the fraction first, and then I'll be writing it in decimal form because that's just a cleaner way to do it. So in order to get this by itself, because we want to find this variable, we need to go ahead and subtract this 1 over 45.7 from both sides. So that's what we're going to do. And yes, you can subtract fractions from one another. Don't freak out just because they're in fraction form. So I'm going to put them in fraction form right now into my calculator. And when it spits it back out at me, I wouldn't be surprised if it automatically gives me something in decimal form. But either way, I'm going to convert it that way. Yeah, it did. So I get 1 over my image distance is going to be 0.044. Okay? And then all I have to do to figure out what my image distance is set it up like this. Okay? I'm just going to switch places right now. I'm going to switch places where I have 1 over 0.044 centimeters is equal to the image distance. So I go ahead and do that. And I end up with an image distance of 22.73 centimeters. So my image distance this time is going to be less than my my object distance. Whoops. Well, that was bad. There we go. There's that first one. And now we're going to determine the image size. So when we want to determine the image size is the same thing as image height. So we know that we're going to take our hi-ho, 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 it's off to work we go. This is going to be equal to negative of the image distance over the object distance. All right, since we have both of these variables and we know our object height, we're going to go ahead and solve for the image size, which is that hi. That is what we are looking for right here. Okay. So just for the purposes of having more room, I'm going to go ahead and erase my diagram right now because I want to have everything on one screen. Okay. So I'm just going to rewrite everything the way that it was. Our object height, or h sub o, is going to be 4 centimeters. Now on top we have negative of the image distance. My image distance before, if we go and look over here, that's the one we had to calculate, and that's going to be 22.73. So we had to calculate that first before we do this. And I also need my object distance. Well, my object distance is just how far away from the mirror it was, so that's our 45.7. And notice how these are both centimeters, so when they cancel out, they're going to leave a unitless number, and that's perfectly fine. As I explained with magnification before, it is just a unitless number that expresses how much bigger or how much smaller your image and your object are going to be to one another. So now we can just cross multiply and divide like you would in algebra. So I'm going to go ahead and multiply negative 22.73 by 4 centimeters. And I'm going to divide that by 45.7 centimeters. And that negative represents that your image is on the other side of the mirror, and that makes sense. So now I see that my image height is going to be equal to negative 1.99. Suppose you could always break it down and round it to 2 centimeters. And so our image height is actually smaller than our object height. Cool stuff here. All right, second problem here, and let me go ahead and make a note on what I said earlier about the image height. So if our image height, or h sub I, is negative, that means we have an inverted or upside down image. Sorry about that. One of those things that just slipped my mind. Okay, just be aware of that. We got a negative answer for our previous problem, so you're going to have an inverted image in that problem. All right, so we have the same 4 centimeter tall light bulb, and it's placed a distance of 8.3 centimeters from the concave mirror, having a focal length of 15.2 centimeters. So this time, it's actually in between the mirror and the focal point. Principal axis, I'm going to expand it a little bit, right, so that I have more room. There's our focal point. Here is our light bulb. We again know that our distance of our image is what we're looking for, and our image height. So that must mean that we have the distance of the object. It tells us that it is placed 8.3 centimeters from the mirror. That must mean that we have the object height, which is 4 centimeters. And that must mean that we have the focal length, which is 15.2 centimeters. Now let's go ahead and solve using our first equation, and then we'll go ahead and solve using our second one. So first one is going to be our 1 over the image distance plus 1 over the object distance gives us 1 over the focal length. Same procedure as before. This time our object distance is a little different though. Still don't know the image distance. There is our object distance. There's our focal length. So do the same thing that we would last time. We subtract 1 over 8.3 from both sides. And whenever we do that, we get an answer of, remember to bring everything down again, right? That means that you have 1 over d sub I is equal to, be helpful if I had done the math ahead of time, right? I get negative 0.05 centimeters. All right. Now I'm going to go ahead and just switch these two, right, to figure out what my image distance is. So 1 over negative 0.05 centimeters is equal to our image distance. And that's going to give us an image distance of negative 20 centimeters. So since this is a negative, right, that means that we are going to have a virtual image. This means that it appears in the back of the mirror, like as if you were to walk through the mirror, you would have the object on the other side of it. So if we have a negative image distance, you have a virtual image. So that solves for our d sub I. We'll write it up here so that we can solve for the rest. Make sure you get all this down. I'm going to go ahead and erase, and we're going to go ahead and solve for our image size or our image height. They mean the same thing. Okay. Using the second equation, we have hi-ho. We also have image distance, object distance. All right, so we know everything except our image size. That's what we're looking for. So everything else gets plugged in. We know that our object height is 4 centimeters. We know that our image distance is negative 20, so we're putting a negative sign on the outside and putting negative 20 out here. Of course, a negative and a negative mean that you're going to end up with a positive. So then we have our d sub O right here. Okay, now we cross multiply and solve. Again, double negative here, that means we're going to be dealing with a positive 20. So whenever I do that, I end up with an image height of 9.64 centimeters. So since this is a positive number, that means it's above this principal axis. This means it's an upright image. And since it's larger than the actual height of the object itself, we would say it's larger than the object. Okay. Make sure you're referencing the notes that you've taken over the 5 different cases that we've discussed over the different types of situations that you can have depending on where the object is in relation to the focal point. Those are going to help you solve the assignment for this week. Again, make sure that you're looking at everything that's been assigned as notes or as a video over the week. That's going to help you with trying to